Recursion, it's basically the secret weapon of efficient data structures and algorithms. But let's be real, for a lot of us, it is incredibly intimidating. In this explainer, we're going to completely demystify recursion. We'll take it from this confusing, abstract concept and turn it into a logical, step-by-step framework. If you have ever stared at a function calling itself and just felt completely lost, hey, you're in the exact right place. Today, we're diving right in to break down exactly how to think recursively, how to trace the call stack, and we'll figure out just how much computational power your elegant code is actually costing you. So, here is our roadmap for today. We'll start with the core concept, move on to designing functions, do some simple dry runs, tackle complex recursion with Fibonacci, solve the classic Tower of Hanoi, and wrap up with complexity analysis. All right, part 1, the recursion concept, breaking down problems. Let's get right to it. At its core, recursion is just a technique where a function calls itself to solve a problem. But listen, it doesn't just call itself at random. It deliberately breaks the main problem down into identical, smaller subproblems. Think of it exactly like a set of Russian nesting dolls. Every time you open up a problem, boom, you find a smaller instance of the exact same problem inside. And you just keep opening them, moving from this massive outer problem to slightly smaller inner ones until you hit the absolute smallest solid doll in the center. In programming, what we do is solve that tiny solid doll first, and then use that answer to build our solution all the way back out. Make sense? Okay, moving on to section 2, designing recursive functions using a simple 3-step process. You can actually design any recursive function by rigidly following 3 steps. First step, define your assumptions. You really have to confidently declare what your function is supposed to achieve before you write a single line of code. Second, map out the main logic. Like, how exactly does the larger problem break down into that smaller subproblem? And third, and pay close attention here, because this is absolutely crucial, identify your base case. The base case is your terminal condition. It's the rule that tells your function when to stop opening those nesting dolls. This delicate balance is really the heart of recursion. On one side, we've got the recursive case, where the function calls itself and the problem shrinks. On the flip side, we have the base case, which returns a direct answer and tells the recursion to stop. It's our safety net. And here is a huge tip for your coding interviews. A super common mistake is missing the base case entirely, or just writing an incorrect one. If you do that, the function literally never stops. It just keeps digging and digging until it crashes your entire program with a dreaded Stack Overflow error. That basically just means your computer ran out of memory trying to hold all of those open dolls at once. Next up, section 3, tracing simple dry runs and tracing the call stack. Let's actually visualize this by finding the sum of the first n natural numbers. When we pass n into our function, the main logic tells us the answer is n plus the sum of n minus 1. Now, because the code encounters a brand new function call, it actually has to pause the current calculation and open a completely new frame in memory. These calls physically stack up until n equals 0. And hey, that 0 is our base case. Once it hits 0, it stops diving and bounces right back up the chain, passing the accumulated sum layer by layer back to the very first caller. It's the exact same mechanics for calculating the factorial of n. Finding the factorial relies on multiplying n by the factorial of n minus 1. If you visualize this trace, you can conceptually see the physical call stack executing top-down. Let's say we want the factorial of 5. Well, it has to wait on the factorial of 4, which waits on 3, and so on. It physically stacks these open operations until our base case of 1 is completely resolved and then cascades that multiplication all the way back up to give us the final result. And this exact same pattern works effortlessly for other linear problems too. Say you want to calculate a power function, like a to the power of n. You just multiply a by the recursive result of a to the power of n minus 1. You just keep decrementing that exponent until it hits a base case of 0, which then simply returns 1. Or think about traversing an array. You can print the element at your current index I, and then recursively call the exact same function for index I plus 1. It is an incredibly elegant way to loop through data without ever having to write a traditional for or while loop. Pretty cool, right? All right, section 4, complex recursion, the Fibonacci sequence. Now, the Fibonacci sequence is where things get really fascinating. In this sequence, each number is the sum of the 2 preceding ones. Because of that, a single function call actually spawns 2 more simultaneous calls. And since it depends on the 2 previous numbers, we actually need 2 base cases here. The Fibonacci of 0 is 0, and the Fibonacci of 1 is 1.
When we call fib of n, the recursive tree physically branches out in two different directions at the exact same time, fib of n-1 and fib of n-2. As we generate the sequence, 0, 1, 1, 2, 3, 5, 8, try to imagine that branching tree of function calls. Because the branches overlap, we're actually forced to recalculate the exact same subproblems over and over again. To find fib of 5, you have to calculate fib of 4 and fib of 3. But to find fib of 4, you have to calculate fib of 3 all over again. This plants a little seed about a hidden inefficiency in naive recursion. Don't worry though, we are absolutely going to address that when we get to complexity analysis. Which brings us to section 5, the Tower of Hanoi, a classic puzzle.
If you haven't seen it, the Tower of Hanoi is a classic computer science problem. Picture 3 rods, a source, an auxiliary, and a destination, and a stack of varying disks. The goal is to move the entire stack to another tower, but you have to obey some strict physical rules. You can only move one disk at a time, and a larger disk can never, ever be placed on top of a smaller disk. I'll tell you right now, trying to write a standard iterative while loop to track all these changing rules is an absolute nightmare. But Recursion? Recursion handles it beautifully.
By simply trusting our recursive assumptions, we can solve this gracefully in just 3 steps. Step 1, recursively move the smaller n-1 disks out of the way, taking them from the source rod and stashing them on the auxiliary rod. Step 2, move the largest nth disk directly from the source rod over to the destination. And step 3, recursively move those n-1 smaller disks from their stash on the auxiliary rod right back on top of the largest disk at the destination. Just 3 lines of recursive logic solve this deeply complex physical puzzle. It's almost like magic.
Let's jump into our final section, section 6, complexity analysis and computational costs.
Here is a crucial interview tip for you. Never, ever present a recursive solution without knowing exactly what it costs computationally. If you can't explain the space complexity, the interviewer is going to assume you don't actually understand the call stack. We measure a recursive function's efficiency using 2 simple formulas. Time complexity is the total number of function calls multiplied by the time taken per call. And space complexity is equally vital. It's the maximum depth of that physical memory stack multiplied by the space used per call. Remember, every single time a recursive function pauses to call itself, it takes up real memory. If your tree goes 100 levels deep, that's 100 frames just sitting there in memory waiting to resolve. Consider the stark contrast in these computational costs. Simple, linear recursion like our factorial or sum of n examples only costs a linear big O of n. That means the time it takes grows at a steady, flat rate alongside your input. The call tree is just a single, straight line down. But those multiple branching problems, like Fibonacci and the Tower of Hanoi, they literally explode into an exponential time complexity of O of 2 to the power of n, because every single node splits into 2 more nodes. The number of calculations doubles at every step. It really demonstrates how rapidly recursion can scale and become a massive performance bottleneck if you aren't paying close attention. Well, we've covered a massive amount of ground in this explainer today, from those basic nesting doll concepts all the way to exponential big O complexities. Understanding this intricate dance of call stacks, base cases, and complexity limits is what unlocks true computational thinking. It is exactly what separates a casual coder from a top-tier algorithmic problem solver. So as you head into your next coding challenge or technical interview, I want you to ask yourself, how will you apply the Russian doll framework to safely map out and conquer your next recursive algorithm? Thanks so much for joining me, and keep practicing those dry runs.